In this video, we're going to cover mechanisms, looking at what the purpose of a mechanism is and how you would draw one. Nucleophilic substitution reactions, so looking at halogenoalkanes, the general process of nucleophilic substitution and the rate of nucleophilic substitution. And finally, looking at elimination reactions. A mechanism shows how molecules react together. Lots of different chemical reactions involve the interactions of several different molecules. A mechanism uses something called curly arrows to show which bonds are broken during a chemical process and which new bonds are made during that process. A curly arrow is used to represent the movement of a pair of electrons in a reaction. A curly arrow will either start at an existing chemical bond or at a lone pair of electrons on an atom. The curly arrow will end where the new bond is formed, and we'll look at some examples of how we would draw these. So to start off with, we've got a generic molecule here. We're going to be focusing on the carbon and the chlorine atom. A curly arrow drawn here would represent the electron pair of the carbon-chlorine bond moving to the chlorine atom. If the pair of electrons, the shared pair of electrons, which is the covalent bond, moves to the chlorine atom, there will no longer be a bond between the carbon and the chlorine. So this kind of arrow represents the breaking of a chemical bond. We can see here, in the second stage, we have now broken the bond between the carbon and the chlorine. These are now two separate. We've got a molecule and an ion here. So we've separated them because the carbon-chlorine bond has been broken, represented by this arrow here. This time, we're going to look at what happens between a carbocation and a hydroxide ion. We mentioned earlier how a lone pair can be the start of a curly arrow, just like it can start at a bond. We've drawn the lone pair here, so we know very clearly where that curly arrow is going to start. In this case, in a moment, we're going to draw a curly arrow between the lone pair and the carbon ion here, representing the formation of a new bond. So we draw the curly arrow as such, showing it starting at the lone pair and finishing at the carbon. And that lone pair has now formed a bond between the carbon and where it started off with, as represented in this molecule here. We've just looked at how lone pairs are the starting point for some curly arrows. A nucleophile is an electron or a lone pair donor. So we're going to look at nucleophiles in lots of different mechanisms, and essentially this is the molecule which attacks or starts the process. So you need to know the definition of a nucleophile as it is an electron or lone pair donor. The OH- ion is a common nucleophile, and you'll see we've very clearly drawn the lone pair on. The Cn- ion, the cyanide ion, is another common nucleophile. It's important to note that the lone pair is on the carbon, so we draw the lone pair here. The lone pair has to be drawn on the atom which has the lone pair. The negative charge just represents the charge for the entire molecule. So it doesn't matter that the negative charge is drawn above the nitrogen because it's effectively there for the entire ion, but the lone pair does have to be drawn on the associated atom. And finally, the NH3 molecule is another nucleophile with the lone pair shown. Nucleophiles commonly will have a negative charge if they're an ion, but they don't have to, because for example, NH3 is a molecule that doesn't have a charge. The first kind of mechanism we're going to look at in a moment is nucleophilic substitution with a nucleophile and a halogenoalkane. Before we can look at that kind of mechanism though, we just need to recap what a halogenoalkane is. A halogenoalkane is a molecule, an alkane, where one of the hydrogens, or one or more of the hydrogens, has been replaced with a halogen. In this case, we're looking at bromomethane. From your work in the physical chemistry topics, you'll have looked at electronegativity. We know that bromine is more electronegative than carbon. We can represent this by writing a delta negative sign here. As bromine is more electronegative than carbon, it will pull some of the electron density within this double bond closer to itself, therefore, as we've just said, becoming slightly negative. This will make the carbon slightly positive. This is important for understanding how the mechanisms work. So in a halogenoalkane, we've got a polar bond here, because the bromine has got more of the electrons from the double bond towards it, therefore it is slightly negative, and the carbon is slightly positive. This means that the molecule is susceptible to nucleophilic attack because we've got a carbon which is slightly positive. This is important because the lone pair on the nucleophile, obviously a lone pair of electrons, is negative, and that negative lone pair is going to be attracted to the slightly positive carbon. So if we imagine we've got a nucleophile here, which has got a negative lone pair of electrons, there will be an attraction between that negative lone pair of electrons and the slightly positive carbon, and this is ultimately what is going to cause the reaction and the mechanism, which we'll look at in a moment. We're now going to look at a general mechanism. So this is kind of like the template mechanism. Before we actually use real atoms or actual examples, we're just going to look at the generic process. So we're looking at something with a CX bond. In this case, X can represent any halogen. So this process would work whether the X was a bromine atom, a chlorine atom, a fluorine atom, or an iodine atom. As this is just a general mechanism, we use X, so you could use this template for any kind of mechanism. It involves a reaction with a nucleophile. Here I've just written Nu to represent any kind of nucleophile. And we're going to show the lone pair as well. We're just going to remind ourselves of the partial charges in this case. You don't have to draw these on when you're drawing a mechanism. If you can remember that they're there, that's great. If you wish to add them, that's up to you. But we know that the halogen is always going to be slightly negative, and the carbon is going to be slightly positive. In a nucleophilic substitution mechanism, the first stage is a curly arrow being drawn between the lone pair in the nucleophile and the carbon atom. This represents the lone pair on the nucleophile attacking the carbon, forming a new bond between itself and the carbon. Now, as we know, carbon can have only 4 bonds. If we were to form a new bond between the nucleophile and the carbon, it would have 5 bonds. That wouldn't be very stable, that process wouldn't happen. So what happens is, after the first curly arrow, we draw a second curly arrow representing the carbon X bond, the carbon halogen bond being broken. Now both of these processes happen at the same time. So in this case, we've drawn both curly arrows on one molecule, so it means both of these curly arrows happen simultaneously. So as the lone pair from the nucleophile is making its way towards the carbon, at the same time, the CX bond is being broken. So this all happens in one step. Giving us a final product where the carbon now has a bond attached to the nucleophile, and we have an X ion separate as it has had its bond broken here. As this is the first mechanism that you've come across in organic chemistry, we're just going to look at what happens in each stage in detail. So the first stage occurs here. This is where the lone pair on the nucleophile attacks the slightly positive carbon. The second stage occurs here and here. This is where a new bond is formed between the carbon and the nucleophile. The third stage is where the carbon halogen bond is broken, forming an X- ion. We're now going to look at the reaction of a halogenoalkane with several different nucleophiles, the first of those being hydroxide ions. When a halogenoalkane reacts with a hydroxide ion, it forms an alcohol. So for example, chloromethane reacting with sodium hydroxide. This would form methanol and sodium chloride. The first stage is to draw out the molecules involved. So we've drawn our chloromethane here, and we've written our hydroxide nucleophile here. You might notice that we wrote sodium hydroxide in the equation, and we've drawn the hydroxide ion down here. That's because in an aqueous solution, the sodium hydroxide, as you'll know from the work you've done on acids and alkalis at GCSE, will dissociate into sodium ions and hydroxide ions. You can't just get a bottle off the shelf of hydroxide ions, it will always be some kind of metal hydroxide. That's because this is the reagent which you would use, and in the mechanism we're just using the hydroxide part of it. The equation has to be the full chemicals you would use. In the mechanism we just showed the reagents which are actually doing the reacting. So we don't need to show the sodium atoms in the mechanism, but we would have to write the full chemical, the sodium hydroxide, in the equation. The sodium doesn't play a part, so we don't include it in the mechanism, but like we said, you can't buy a bottle of hydroxide ions, it would have to be sodium hydroxide or potassium hydroxide, but the mechanism just focuses on the part of the chemicals which actually do the reaction. We'll then draw on our lone pair for the hydroxide, as it's our nucleophile in this reaction. We would either draw on or mentally remember that the halogen is going to have a partial negative charge, therefore the carbon will have a partial positive charge. The first arrow starts at the lone pair, ends at the carbon, representing a new bond being formed between the carbon and the oxygen. The second arrow represents the breaking of the carbon-chlorine bond, starting halfway between the carbon-chlorine bond and ending on the chlorine. This will give us our final product, where we've now got the carbon attached to the OH and a chlorine which is negative. The reason the chlorine is negative is the shared pair of electrons, so one from each atom, has now ended up on the chlorine, so it's got one more electron than it started off with, therefore it has a negative charge. The reason the OH has lost its minus charge between here and here is because originally it had one more electron than it would normally have, which is why it had a negative charge. That extra electron has essentially formed the shared pair now between the oxygen and the carbon, so each atom now has the correct number of electrons, which is why there is no negative charge there. In mechanisms, it's important to remember that the total charge on each side will be the same. So in the first step, there was one negative charge overall. In the second step, there is still one negative charge overall. If your charges don't match up between each side of the equation, it means you've probably made a mistake somewhere and will need to go back and review what you've done so far. When a halogenoalkane reacts with a cyanide ion, it will form a nitrile. So for example, bromoethane reacting with potassium cyanide will form propane nitrile and potassium bromide. Remember, the carbon in the nitrile group does count towards the overall chain length, so when you're doing equations with nitriles, be careful that we've started off with an ethane stem, and we've now ended up with a propane stem. The first stage to draw the mechanism is to draw out both of the molecules, remembering that it's the cyanide ion that we're interested in, so we don't include the potassium. So potassium cyanide is the reagent, the cyanide ion, it is what's involved in the mechanism. We'll draw on the lone pair. We'll either draw on or remember that the halogen, the bromine, is going to be slightly negative, the carbon is going to be slightly positive. We'll draw the first curly arrow, starting at the lone pair, ending at the carbon, representing a new bond between the carbon and the carbon. And the second curly arrow starting in the middle of the carbon-bromine bond and ending on the bromine. representing the breaking of that bond. Given as a final product of our propane nitrile, with a new bond between the carbon, and the bromine no longer attached as its carbon-bromine bond was broken. Again, remembering that we've now got one negative charge in total on the left-hand side and one negative charge in total on the right-hand side. When a halogenoalkane reacts with ammonia, it forms an amine. So for example, chloromethane reacting with ammonia would form methylamine and, in this case, ammonium chloride. This equation is slightly different from the ones we've looked at so far. You might notice we have a second ammonia molecule involved, and we form an ammonium salt rather than a simple salt like we've looked at in the previous examples. We'll explain why as we look at the mechanism and the process involved in this reaction. So as before, we'll start by drawing both of the molecules involved. We'll add the lone pair onto the ammonia. We'll draw the first curly arrow as normal from the lone pair to the carbon, representing a new bond being formed between the nitrogen and the carbon. And then we'll draw the second curly arrow representing the breaking of the carbon-chlorine bond, starting in the middle and ending up on the chlorine. Now we've made a new bond between the nitrogen and the carbon, as shown here. However, nitrogen normally has 3 bonds. Nitrogen has 5 outer electrons, so 3 covalent bonds will take it up to a full shell of 8. By making a new bond between the nitrogen and the carbon, we've essentially given nitrogen 1 extra bond than it wants to have. Nitrogen now has 4 bonds rather than the 3. This would make it unstable. As it has got 1 extra bond, we've drawn a positive charge to represent this, and we're now going to look at the next step in the mechanism about how nitrogen can lose one of its 3 hydrogens, so it's only got 3 bonds, therefore becoming stable again. So to lose one of the hydrogens, to break that nitrogen-hydrogen bond, we show that by drawing a curly arrow going from the middle of the nitrogen-hydrogen bond to the nitrogen. Therefore giving us a H+ ion by itself, a chloride ion, and the nitrogen now only has 3 bonds again. This has kept the total charge the same. We've got no charges over here, and at the end of this process we've got a negative and a positive charge, therefore cancelling each other out, representing no charges at the end. Now this is why we've got 2 lots of ammonia in the mechanism and we've formed the ammonium chloride salt. We've formed a hydrogen ion during this process. If you remember from your work in GCSE, H+ ions are what essentially acids are. It's a proton, it is what an acid is, a H+ ion. Ammonia is a base. Ammonia will react with a hydrogen ion to form the ammonium ion. This is why we need to have 2 equivalents of ammonia in our equation. A chemical will always react with other chemicals around it if it can. The chemicals won't think to only react with the chloromethane. As soon as the very first ammonia molecule reacts with the chloromethane molecule, it will produce an acid molecule, a H+ ion. As soon as the H+ ion is formed, it will react with some of the ammonia, which hasn't yet undergone this process, to form the ammonium ion. Therefore, if we didn't have twice as much ammonia as we do chloromethane, we wouldn't make 1 mole of the product, because if we just had 1 mole of the chloromethane and 1 mole of the ammonia, you'd probably end up making about half a mole of product, and you'd make about half a mole of the ammonium chloride. So in order for the reaction to go to completion, you need twice as much ammonia as you do chloromethane, because you need 1 ammonia molecule to react with the chloromethane and 1 ammonia molecule to react with the hydrogen ion, forming the ammonium chloride final product. So because of this reaction here, you have to remember when writing out the equation, you need 2 lots of ammonia and you will form the ammonium chloride salt. If we look at our product from that reaction, in this case methylamine, the nitrogen has a lone pair, just like the ammonia did. This means it can react with halogenoalkanes in exactly the same way as the ammonia did. So amines can react just like ammonia. So for example, we've got our halogenoalkane again, and this time I've drawn the product from the reaction we looked at a moment ago. We can add the lone pair onto the nitrogen. We can draw our curly arrows from the mechanism, starting at the lone pair on the nitrogen, ending on the carbon, representing the formation of a new bond, breaking the carbon-bromine bond by starting in the middle of the bond and drawing a curly arrow ending on the bromine. Giving us our product, noting the positive charge on the nitrogen as it's got one more bond than it would normally have. Drawing our curly arrow to show the removal of the hydrogen through the breaking of the hydrogen-nitrogen bond. Giving us our final product here. And again, in theory, this molecule could react again with another halogenoalkane as the nitrogen still has a lone pair. You'd look at this process in a lot more detail in year 13 in the amines topic, but just be aware that amines can react exactly the same way as ammonia does, because the nitrogen still has a lone pair. We're now going to look at what affects the rate of reaction of different nucleophilic substitution reactions. In order to do this, we're going to look at the type of bond and the bond enthalpy. Remember from your work in physical chemistry that the bond enthalpy essentially represents the strength of the bond, how much energy is required to break the bond, or how much energy is released on the formation of that bond. So we'll look at the different bonds in order of going down group 7. So we've got the carbon-fluorine bond first, carbon-chlorine bond, carbon-bromine bond, and carbon-iodine bond. And then the bond enthalpies of those bonds. So we can see that carbon-fluorine bond has got the highest bond enthalpy, carbon-iodine bond has got the lowest bond enthalpy, therefore the carbon-fluorine bond is the strongest, and the carbon-iodine bond is the weakest. You don't need to know why this trend exists, you just need to know that the carbon-fluorine bond is the strongest, and the carbon-iodine bond is the weakest. Therefore, as you go from the carbon-fluorine bond down to the carbon-iodine bond, the bonds are easy to break because the bond enthalpy is lower. Therefore, the rate of substitution will happen at a faster rate. So you'd expect the rate of reaction of a molecule with a carbon-iodine bond would happen a lot faster than a molecule with a carbon-fluorine bond. We're now going to look at a different kind of mechanism which halogenoalkanes can undergo. So we looked first at the nucleophilic substitution reaction of halogenoalkanes with hydroxide ions, cyanide ions, and ammonia. We're now going to look at a different way they can react with molecules, this one being the elimination mechanism. And this results in the halogenoalkane being turned into an alkene. Similar to nucleophilic substitution, an OH- ion, a hydroxide ion, is involved in this mechanism. However, in the nucleophilic substitution mechanism, the OH- acted as a nucleophile. In this mechanism, it's going to act as a base instead. And when we look at the mechanism, I'll make that distinction clear. So we'll look at the general mechanism first. In this case, remember that X can represent any halogen. So the X could be fluorine, chlorine, bromine, or iodine. I've drawn out, in this case, for example, this could be bromoethane or chloroethane. And I've got my hydroxide ion drawn here, and I've shown the lone pair. In an elimination mechanism, the first stage is for the lone pair to attack a hydrogen ion on the carbon adjacent to where the halogen is. So this first arrow could have gone to this hydrogen here, this hydrogen here, or this hydrogen here. It can attack any of the three hydrogens on the carbon adjacent, so next to the carbon with the halogen. So we're going to form a new bond in the first step between the oxygen and the hydrogen. At the same time as that is happening, we break the carbon-hydrogen bond and we form a double bond between the carbon and the carbon. We represent this by starting our curly arrow between the carbon and hydrogen bond and ending it in the middle of the carbon-carbon bond. Finally, all happening simultaneously, we break the carbon-halogen bond just like we did in nucleophilic substitution by drawing a curly arrow going from the carbon-halogen bond to the halogen. So to recap what has happened, we've got a new bond between the oxygen and the hydrogen. We've broken the bond between the carbon and the hydrogen and made a double bond between the carbon and the carbon and broken the carbon-halogen bond, leaving us with an alkene, in this case ethene, because we started out with some kind of halogeno-ethane molecule here. We formed water because the OH- has gained a H, and we've got a halogen ion by itself. This is why the OH- acts as a base rather than a nucleophile. In nucleophilic substitution, we formed a new bond between the nucleophile and the carbon, so it was acting as a nucleophile. It's now acting as a base because it has removed a hydrogen. Remember, hydrogen ions are an acid, therefore we say the OH- is acting as a base. And this is why this mechanism is different to the nucleophilic substitution mechanism we looked at earlier in this video. We'll now look at a worked example of this process. So we'll start off the example by drawing out both molecules. In this case, I've drawn out bromopropane and I've got my hydroxide ion here. As usual, I'll add in the lone pair. I'll draw in the first arrow, so going from the lone pair to a hydrogen on the carbon adjacent to the carbon with the halogen. So I could have drawn it to the hydrogen up here if I wanted. Couldn't draw it here because this isn't a hydrogen, this is a carbon attached to the carbon. So I have a choice of any of the hydrogens on the carbon adjacent, so next to the carbon with the halogen. My second arrow is from the carbon-hydrogen bond to the carbon-carbon bond, which will make it into a double bond. And from the carbon-bromine bond to the bromine. Remember, all these arrows happen simultaneously. So as the first lone pair is moving up, we're breaking this bond at the same time as breaking this bond. Giving us a final product of this alkene here, which we followed through by removing this hydrogen, adding a double bond between these carbons, and removing the bromine. We're now going to look at a different example where something a little bit strange might happen. So this molecule, just like before, has got 3 carbons in its chain, but on the second carbon, we've got an amine group and an alcohol group. We'll draw out our molecule with its lone pair. However, this molecule can't actually undergo elimination. If we have a look at what the first step should be, an arrow going from the lone pair on our hydroxide to a hydrogen on the adjacent carbon, well, the adjacent carbon, this one here, because our halogen is on this carbon, so the adjacent carbon is this one, there is no hydrogen bonded to this carbon. Bonded to it directly is a nitrogen, a carbon, or an oxygen. No hydrogen. Therefore, there is no hydrogen attached directly to the adjacent carbon we can remove, therefore no mechanism can take place. I'm showing you this example because some exam questions will ask you to draw a molecule which can't undergo elimination, and when we look at more chemistry and some further topics, sometimes questions will ask you to draw molecules which can't undergo certain processes to help you figure out the next stage in a wider process. So this is just worth bearing in mind that if you're asked to draw a molecule which can't undergo elimination, it means there can't be a hydrogen on the carbon adjacent to the carbon with the halogen. We're now just going to summarise the conditions used to make a reaction either go for nucleophilic substitution or elimination, because both of these processes use the same hydroxide ion. Because nucleophilic substitution uses OH-, as does elimination. In order to make the OH- act as a nucleophile, you'd have to do the reaction in aqueous conditions. This means you'd do the reaction dissolved in water. In order to make the OH- ion do the elimination mechanism, you'd have to do it in alcohol conditions, or called ethanolic conditions. So rather than dissolving your chemicals in water, you dissolve them in ethanol instead. Therefore, in aqueous conditions, the OH- acts as a nucleophile, and in alcohol conditions, or ethanolic conditions, the OH- will act as a base.